Hi, welcome back. Let us continue our discussion on coordinate systems, and in this video we're going to look at cylindrical coordinates. Alright, so I've got this picture up here that I've pre-drawn because it takes me forever to draw figures that look this good because I'm not an artist. But you'll see that I've got the x, y, z coordinate system, and I've got this point P, or I guess I haven't labeled the point, but I've got this point here. And it seems to be kind of somewhere on this like broken up cylinder. And you'll see in blue that, or I guess before that, you'll see in green, I can locate that point with these three numbers in green, right? I can tell you how far, that's this arrow or this line here, how far the point is from the z-axis. Okay, so that's rho, the Greek letter rho. It looks like a P, but it's rho. So I've got rho. So I can tell you how far it is from the z-axis. Then I can tell you the angle it makes with the positive x-axis. Okay, and that's this Greek letter phi. Then, once I tell you how far away it is from the z-axis and what angle it makes from the x-axis, I have to tell you how high, or how far up and down it is to this point, and that's the z-coordinate. So that's the regular old z-coordinate. Okay, so I need these three numbers to specify a point in cylindrical coordinates, just like in rectangular. I needed the three numbers x, y, and z. All right, so and you'll notice z comes up in both cases, and there will be no funny business in this video in cylindrical coordinates for the z coordinate. And what I mean by that is that the analysis for the z coordinate does not change at all when you go from rectangular to cylindrical. Now, as we said, rho is the distance from the z-axis. So rho can take on values between 0 and infinity, including 0 actually. So if it lies exactly on the z-axis, then that would be a rho of 0. So you can think of a rho as kind of like a radius. And phi is the angle that the point makes with the positive x-axis. So phi can actually take numbers between 0 and 2 pi. And because it goes all the way, it could go all the way around the x-axis. And I want you to notice a subtlety here that we're not including 2 pi. You'll never have a phi of 2 pi, and that's because 2 pi and 0 are the same angle. And in order to be able to uniquely specify a point, then we can only include either 0 or 2 pi, and the convention is to include 0, not 2 pi. And z, again, is this regular old z coordinate, and just like in rectangular form, z can go from minus infinity to positive infinity. In rectangular form, x, y, and z all can go from minus infinity to positive infinity, as you know from dealing with rectangular form quite a bit. And so in cylindrical coordinates, we can represent a vector A with these three numbers, right? With their components, we would say that it would be a rho. So a rho is this distance from the z-axis, and a phi is the component along the phi direction, and then az is the component in the z direction, so this would be cylindrical. Just like in rectangular form, we could represent that same point as its component in the x direction, its component in the y direction, and its component in the z direction. Or we could use basis vectors, right? So now you'll see my figure in blue extending from this point. I've got the basis vectors a rho, a phi, and a z. Now, as we talked about in the previous lecture video, to be a good basis set, they have to be orthonormal, which means they have to be mutually perpendicular and have a unit length. So you'll see, and it's hard to picture this in 3 dimensions, and I'm going to draw different pictures in a second. But a row extends in the row direction. So it as if we were to extend this green row line, that's the direction of a row. A phi, as you'll see in a little bit, is actually tangent to the cylindrical piece there. And then AZ is the normal AZ. Meaning it's the usual or the typical AZ. It points up, and they have unit length. And so we can represent any vector in cylindrical coordinates as its row component times the basis vector in the row direction plus its phi component times the basis vector in the phi direction plus its z component times the basis vector in the z direction. So this would be cylindrical, just like we could alternatively express that point with its x component in the x direction plus its y component in the y direction plus its z component in the z direction. Right, this would be rectangular. All right, so we've got that, and then being that these basis vectors are still of unit length, we can still talk about the norm or the magnitude of our vector as being the square root of each component squared. So this would be a row squared plus a phi squared plus a z squared. That still gives us the length of that vector, and that's actually one of the reasons why you want an orthonormal basis set. Okay, now let's look at this figure a little bit more carefully, and what we're going to do is we're not going to change the location of this point, but we're going to look at it in different viewpoints. So the first viewpoint that I want to look at, as if we were standing on the z-axis looking down. Okay, so if that's the case, Control Z, my friend there. Okay, if that's the case, if we're on the x-axis looking down, we might have the y-axis there, and the x-axis there. So you can imagine we're looking down now. So we would see our point somewhere like this. And then there's this arc that I've drawn in the original figure, right? That's not a good arc. Okay, something like this. And I've got this green line rho, so there's the rho coordinate, right? And then here's phi, right? It's measured this direction. And you can't really see the coordinate z because we're projecting down the z-axis. So what you can see, though, also is here is the basis vector a rho. So a rho is in the rho direction. It extends out, and we said that a phi is perpendicular, orthonormal, right? And so this is actually the direction of a phi, so that this makes a right angle. And so based on what you learned from math and what you learned in physics, it's always going to be the case that a phi is tangent to this arc, so that it makes a right angle with the radius vector. And our AZ, our third basis vector, is coming out of the page at you because, again, we're looking from the viewpoint of the z-axis. All right, now let's take a different viewpoint. Let's say that we're looking down the y-axis. So in the original figure, let's say we're standing, over here, and we're looking this way. What you would see then is the x-axis would look. Take more care here. The x-axis would be to the left, and the z-axis would be up like that. Okay, so this is looking down the y-axis. So our point that we would see would be somewhere over here, right? And let's think about these lengths. First of all, the height, of this thing is just z, right? That by definition, that's the height, that's the position along the z-axis. But I ask you to consider and think about it. Really think about this. Pause the video if you want. What is this distance? How far along the x-axis are we? All right, well, hopefully you pause the video, but if not, I'll tell you, or even if you did, I'll tell you that it's rho times the cosine of phi. That's that length. And why is that the case? Well, come back to the original figure and imagine this point, moving around the phi direction. So moving around the perimeter of this thing. If phi were 0, then it would be on the x-axis, and the length would be rho. So that would be rho cosine of 0, which would be rho. And let's say you have a phi of 90 degrees, so it's on the y-axis. And so if you're looking down the y-axis, you would see your point right here. And so the distance would be 0, and the cosine of 90 degrees is 0. So that's the distance along the x-axis, rho cosine of phi. And also in this picture, you can see is AZ. That's the direction of our basis vector AZ. Now we can also stand, on the x-axis and look down the x-axis, and what we would see here, the z-axis pointing up, the y-axis pointing to the right, and our point would be somewhere over here, and we've got this length and this length. This length up and down is still z. That's by definition, that's the height along the z-axis. And this length, but with the same or a similar argument as before, this length actually is rho sine of phi. That's the y-coordinate. Okay, and again, our basis vector AZ points up. So those give you three different perspectives of this original figure, what I'm trying to draw in 3 dimensions. So now, as usual, a rho, a phi, and az are of unit length, and their directions are such that they're all perpendicular. So remember, that makes an orthonormal basis set. So we can talk about things like the dot product, a rho dotted with a phi is equal to 0. Why is that? Because a rho and a phi are perpendicular. Okay, in fact, since they're all perpendicular, again, just like what we saw in the Cartesian coordinates, the dot product of any 2 different basis vectors is equal to 0. So, for another example, a rho dotted with az would be 0. When you dot a basis vector with itself, just like what we saw in Cartesian coordinates, you get 1 because they have unit length. So for example, AZ dotted with AZ is equal to 1. Okay, now, and there are other examples. I'll let you work those out on your own, but we're going to move on and talk about the cross product. So this is also a right-handed system. So it follows the same ideas that the Cartesian coordinate system followed. That is to say, for example, a rho cross a phi gives you a z. So let's try that with our right hand. So you should do this. So we'll take this point. You want to point your right hand fingers in the direction of rho. So if you're looking at this original figure right here, you have to kind of finagle your arm and your elbow so that your fingers are kind of coming out of the screen. So now you've pointed your fingers coming out of the screen in the direction of rho. Now you curl your fingers in the direction of phi. So, think about how phi is defined. Phi is in this direction. So you kind of curl your fingers into the screen, and your thumb then is left pointing in the result. That should be pointing up. So that's a nice exercise to do, physical and mental exercise. And you convince yourself also that a phi cross a z is equal to a rho, and also convince yourself that a z cross a rho is equal to a phi. Okay, so that makes another right-handed coordinate system. All right, so I'm going to erase this, and we're done talking with the cross product, done talking about the cross product and the dot product. Now, let's talk about converting between the two systems, cylindrical coordinate system and the Cartesian coordinate system. So if you're given cylindrical coordinates, so if you're given a point, so this is, I just want to specify this is for points. Like we have a point here, so we have rho, we have phi, and we have z. Right? How do we get x, y, and z? So that that would be going from cylindrical to rectangular or Cartesian. So how do we get x, y, and z? Well, we already kind of talked about it, where here in this figure right here, the x coordinate is given by rho cosine of phi. So right away we see, well, if you give me these three numbers, x is rho cosine phi. And similarly, y, the length in the y direction is rho sine phi. So what about z? Well, remember we started this video and we said, well, z is the ordinary z, right? So z doesn't change here. Nothing is changing with z. So that's how we can convert from cylindrical to rectangular or Cartesian. And based on what you know about trigonometry and geometry, it shouldn't surprise you going the other way now. Let's say you're given x, y, and z, and based on what we just said now, you can convince yourself that the way you would get rho, phi, and z, well, you can use the Pythagorean theorem to get the radius rho, that's x squared plus y squared. And you can use that inverse tangent, remember that from physics, to get phi, inverse tangent of y over x, to get phi, and z stays the same. Nice. So this is how you would convert a point, right? Given a point in one system, find that point represented, same point, but just represented in a different way. All right, so now let's talk about how you would convert vectors. So I'm going to erase that. Feel free, I'm going to also erase this. Feel free to stop the video, pause the video if you need to. All right, so let's take a look at, I guess I didn't need to erase that, but I want to make this a little bit bigger. So let's take a look at that point. Again, like we're standing at the top of the z-axis and looking down, so you'll see the y and the x-axis, and our point is like right here or something similar, right? And so I've got this point like this, right? And this is phi, right? The angle that it makes with the x-axis. And we said that this is the direction of rho, not rho, phi, right? That's the a phi. This is the direction of a rho, like that. Okay, and I'm also going to note this is the direction of a negative a phi, right? It's the reversed a phi. And then in blue, this is, I guess it's not that long. try to keep it to scale here. Actually, I'm gonna exaggerate its length because we're gonna have to show some detail. This would be AX, right? A unit vector along the x direction. All right, so what we want to do is figure out, given these basis vectors, a rho and a phi, given the basis vectors in cylindrical coordinates, how do we get AX? Okay, so we're trying to find AX given our basis vectors in cylindrical coordinates. So first of all, you'll notice if I draw kind of a right triangle here, we're going to have to show a little bit of detail here. And from geometry, interior angles, this is also phi. Okay, and so if I take minus a phi times the sine of phi, that gives me this vector. Again, think about trigonometry, sine is opposite. So I'm going to write that down actually. Minus sine phi times a phi. So I took this vector a minus a phi, take the sine of phi, and that gives me the green. Now, notice that, let me just draw another triangle here. All right, and again, from, I think it's alternate interior angles, but from geometry, we know that that's also phi. And this is actually, I didn't draw this well, but this is also a phi. Like if we took this line here, this vector, I guess it should be a little bit longer, and we moved it over here, tip to tail, that would be a phi here. So now if we take a phi and we take cosine of this angle, we would get this vector, cosine of phi. That would give me the orange. And so the sum of these two things, then, the green and the orange, makes AX. So all of that is to say that AX is a rho cosine phi minus, I guess let me put this in a different way. Let's do this. Cosine of phi in the rho direction, right? And minus sine phi in the phi direction. Okay, so that is the result, and that is the way that you would convert one basis vector to, or that is the way you would convert to get one basis vector in the rectangular coordinates. And you can make a similar argument. For brevity, I'm not going to show you the details here, but AY ends up being sine phi a rho plus cosine phi a phi. Okay, so those are two things that we want to be concerned with. And what about that third basis vector? Well, nothing's really changing. Nothing's going on in the z direction. So that basis vector stays the same. So this is if you want to go if you're moving from the cylindrical coordinates to rectangular, and you have a vector. And what we can do, since these things multiply the components, what we can do is write this in matrix form. So this is a kind of nifty time saver. We can get the components of our vector if we put all of this in a matrix, because again, they multiply, the basis vectors multiply our components. So let me put this in a vector, or let me put this in a matrix. Sine, cosine, 0, and then 0, 0, 1 for the z dimension like this. Let's see. Excuse me. This should be AX, AY. Oh, I got this backwards. So if I'm given cylindrical, and I want to get rectangular, if I'm given cylindrical and I want to get rectangular, okay, so from cylindrical, then I use this matrix here, and I can just perform this operation and get my components in rectangular, in one calculation, in one matrix calculation. And I can take the inverse of this thing depending on how much you know about linear algebra, but we're not going to prove the inverse in this course. The inverse of that 3 by 3 matrix is cosine phi sine phi 0 minus sine phi cosine phi 0 0 0 1. And so this is the way you get two cylindrical coordinates. So if you're given rectangular components, you perform this operation and then you get your cylindrical coordinates there. All right, so that was a lot, and we still have one more coordinate system to talk about. So this was cylindrical. We're going to move now to spherical. So if you're still kind of uncertain, or if you didn't catch all of these details, yeah, let me back up, I guess. Let me say that if you did not catch all of these details, that's okay. Should you memorize all this stuff? No, do not memorize this stuff. Write it in your notes, or bookmark it in your textbook, or what have you. But this is good to have on hand, but you should not be memorizing it. Okay, I just wanted to show you how these things come about, and we'll apply them later on in the course. But we still have one more coordinate system to look at, and that's spherical coordinates, and that's coming next.